science session, and a problem set, like in the old days, exams, and we have a master problem solver over here who can solve all your problems in the case, but you must make an effort first. Okay. Okay, where are we? Okay, so we're going to do discrete RG analysis in preparation for some theorems. So the first problem we have to deal with is the fact that although the local potential is additive and therefore its exponential is multiplicative when you have to over disjoint sets, after one iteration is no longer true. So people discovered this marvelous representation which is stable under the renormalization group, in which only a local part is held in the exponential that carries all the information on relevant terms, and everything else which is irrelevant is not exponentiated. And this is a polygon representation. Okay? So since we are working in the continuum, so we pave the continuum with unit blocks, which are cubes or hypercubes. And then, as finite set have the finite volume in it, it has induced paving. So a polymer X is a connected subset of blocks. Everything is connected in what I would say. Connected polymers. And we have this luxury of working with connected polymers because of this finite range property, which we will see. We never have to deal with disconnected polymers and exponential decays and so on. So that's what it is. So polymer activity is a map, a local map, because all the phi's are restricted to x. X phi to kx phi is a function of that, okay? Now, how do I go up?
You have to go to full screen, I think.
Full screen. Yeah. Full screen. View.
Yes.
A little better. So this is a representation. At the generic step, after we had made a scale transformation, so that we went from a covariance with an epsilon cutoff to a unit covariance, and the price we paid for that was, of course, there's a unit covariance, a unit cutoff, and huge volume. And when you go down iterating, because every time you rescale, you come to then capital N is the original volume, torus, and side length L to the N, and after N steps, it becomes that. Okay, so, and this is the representation I've chosen, that this is sum over this polymer disjoint connected polymer activities, and XC, sorry.
So you want to get the red dot?
Yes, I'll get it. Get it yet. Okay? It's a complement of the union of all the xj's in this volume, lambda n minus n. And the local potential will depend on the evolved coupling constants. And we have to find out how they evolve and mass parameter. Now, I claim this representation is stable under the renormalization group. Actually, we started working this in long ago when I wrote my paper with David, and it's earlier with Dimmock. Did you have needed your minus v? Yes, you did actually.
It's been around a long time, statistical physics. We were not the first at all.
So the nth RG transformation uses a map. which goes from Kn minus 1 to Kn. Now the subscript n minus n, I put it in the map because it's not an autonomous map. It depends on what n is. But the whole idea is we're going to take limits, at least as far as this talk is concerned, it's called the formal infinite volume limit, that if you fix a polymer activity to be x, polymer x, then this limit exists. And this you can prove, okay? For a fixed x, the Kn, because V, capital V, is really given by blocks, okay? So you don't worry, it's additive, and Fn minus n. So we will look at these polymers in Rd itself, Rn itself. This is the point for us. So now we're going to do the renormalization group transformation. So the density depends on okay, I have to choose. And we integrate with the fluctuation measure. So we replace phi by phi plus zeta in V and Kn. And we prepare the integrand bit for actually doing the integral. So this is a local potential. What we do now is to consider this as a product, since it's local over all the blocks in the set XC. And then we write this as the difference of Vn and V tilde over there plus the V tilde. Now the important point over here is that this does not depend on zeta, which is the fluctuating variable. Okay. So that's why it's no longer whereas this is zeta plus phi, this is just phi. So that's why we're writing zeta comma phi. Now we expand out and glue together the Pn deltas, okay? This will create new polymer activities. And we will remember that the fluctuation covariance gamma sub L has finite range L. So we should put, it's natural to put together all these one polymers which shall be joined up together, disjoint connected L polymers built out of connected L blocks. Okay, so we call it taking the L closure. That is, you have everything built and you go to the next scale. The reblocking operation is a nonlinear map. But the essence is captured by its linearization. Okay? And we define the linearization this way. So if X is a connected one polymer, its L closure will be denoted by X bar L. It's the smallest connected L polymer which contains X. Then we can define the linearized object by B1 K of Y, which is equal to the sum over all the one polymers such that its closure is Y. And that's what it is. That's clear. And so this I wrote down only. Yes, please.
Linearized?
Yes.
Why it's linearized?
Because this is a highly BKN that I've written here, strip BKN, is a nonlinear object. When you glue together, you have to glue together a lot of things, right? And then after gluing into L, taking the L closures, you have to get its connected components and choose the connected components. It's a nonlinear operation. So this is the, I could write down the formula, it didn't. This exists, I had it and I took it away.
So he's saying he's looking at the linear one because he's looking at the case where there's only one polymer inside the closure. I mean, inside the block.
And the second reason is if you can control the linearized part, the nonlinear parts are very small. So all the trouble is with the linear part. Okay? Now the fluctuation map, which I have, which is the convolution with respect to mu gamma n and then rescaling, it integrates out the zeta and then rescales. However, Vn, if you look at this, this is independent of zeta, so it's right there. Okay, and since it's on the closed L closures with connected L polymers, that is on scale L, you go on adding then all the polymers so that it's finally closed. the disjoint on the scale L and the gamma n vanishes for greater than equal to L. That's a finite range property. Okay, so when I take the fluctuation integration of this and rescale, it will sit inside the product. So, so that's important. The finite range makes it possible to do that. Otherwise, things will decay, and then you have to do some cluster expansion, etc. Okay. Okay. So the fluctuation map integration plus has given a map that is Vn, V tilde n goes to the scale rescaled SL, which is what I've written down. And the polymer activity has been gone to the fluctuated polymer activity, which is really, I've written the full reblocking operation over here. Over here, zeta SL5, but that's the final rescaling that we did and integration. So, but this is not enough. Now we have to extract out things which are growing. How will you do that? We realize that this V tilde was something local, but we choose at our choice. So we can change V tilde if necessary in such a way that the polymer activity that is there has all the growing parts removed. And this procedure is called extraction. So what a change in V tilde produces a change in the FK. So for expanding parts of this, which we'll see how to calculate, we absorb them in B and L, thus producing a flow of parameters, discrete flow of parameters. And the new subtracted polymer activities will have good contraction properties, and provided you set up appropriate norms. And this procedure is known as extraction, which we'll consider a little bit more. So this subtraction operation has only to be done on small sets, and later on I'll explain why that is the case. Because large sets, which has a technical definition, has itself carries contraction factors. This is what Wilson thought always, that the large sets are not very important. I don't know how explicitly he said that, but everything is in the local potential. Okay? And local potential is essentially measured by the blocks. I mean the sets, because it's a union of blocks. So So how will we do this? So we have to define what relevant parts are. What will play the role later on, what you have to subtract and then replace in the potential. So
maybe, maybe V tilde, I don't know whether you said it, is completely arbitrary.
yes, completely arbitrary.
You could choose any V tilde you like in doing that operation.
Including the running coupling constants.
Yeah.
Yeah, but I'm assuming the coupling constants are given at a step, and I'm looking at the next step. Okay, is produce a change in coupling. So we assume that it's a local polynomial. Okay, and where does P run over? It runs over 1 because it can run over phi squared, phi fourth, and intermediate steps also on phi d mu phi. This goes away when I consider, no, not here, not in V, but when I consider on the polymer itself, on F, you'll see. So this is it. So alpha P of X is this, and alpha P of X has a property that it vanishes if X is not an interior of X, and it's also 0 if X is not in lambda. Okay. And the corresponding change in K is given in terms of F of X, this is the relevant part, okay? F of X and F of X delta. Okay. And the formula is given V of F0, because there are also field independent relevant parts, and they will extract out outside of the integration region, okay? I mean, they'll divide out in the Schwinger functions, okay? So I won't pay much attention to them, but they have to be subtracted out. So in the polymer representation, we have a map. V goes to V prime F at 1, because there's also VF0, which will go out, and which is just a difference of that, and K goes to the extraction. And here again, I've written a linearized form. It's a nonlinear formula, which can be controlled, but the linearized form is the most important, which is K minus F, the F0 plus F1 e to the minus V. That's it. That's the linearized form. So we have to compute what this should be.
Linear in K.
Sorry? Linear in K.
Can you show me what is F1?
F1 is the field dependent part.
Yeah.
And F0 is the field independent part. It's always there.
Yeah, but what is the difference between VF1 and F1?
Oh, BF1 and F1. Then, I'm sorry, K goes, it should be VF1. VF1 prime I've written is V minus VF, but that should be VF1, you're right.
Where?
In the mapping, V goes to.
Hold on. Yeah, this
Oh.
way. Okay. This should be VF1, okay?
Okay.
Sorry. And VF0 is a constant contribution. It's a so-called vacuum energy, and because it's not supersymmetric, it is there. It will divide out. Okay, so this is there. So how shall we fix this? So I will. So a general using second-order perturbation theory, as we will see, I'll give you an explicit form of what this Qn is, and you get a remainder which is third order and beyond, which are irrelevant terms actually. And we will see that this Qn depends on the fields. It depends on an kernel. It's a non-local thing, which W, which iterates out to a fixed point, okay, which is W star. It's an autonomous evolution of W. So this is how you fix the constants. You'll say that a polymer activity J is normalized if for all small sets, and I haven't defined that, have I? Yes, X,
Maybe right.
the number of sets connected polymers of size less than 2 to the power of D.
Maybe we should write that on the blackboard, because that's an important definition for this whole thing.
And by default, it's a connected polymer. It can be a block, it can be 2 blocks, and when D is 3, it can be up to 8 blocks, okay, in all possible ways, connected. Okay, so these are normalization conditions. I had to fix these, the J's, which are the subtracted well, okay, for any polymer activity J is normalized in that way. If it's normalized at all, those are the normalization conditions. And then we will apply this to this thing.
What's the x mu?
Sorry?
What's
X mu
yeah?
is a direction.
Just the polynomial.
Just the polynomial.
It's the linear.
Those are the directions. Those are the directions in which I'm taking the derivatives.
So those are unit directions, right?
Yes.
Yes.
One is the unit direction.
One. Right.
Okay.
Oh, I see. So it means you differentiate in this, in the third line, you're differentiating twice the polymer.
Once
activity
with respect to
with
one,
respect to the field in the direction of a constant field, which is 1,
and the other X mu.
and the other is in the direction of a polynomial field x mu.
So it's dependence in the derivative of the field.
So
It's dependence in the derivative of
it's the semicolon means that after the the x tells you where the polymer is, the polymer. The
Zero
tells
is
you
the
that
field is zero.
is set to 0.
Zero.
The 1 tells you you're going to differentiate
In the
field
direction 1.
dependence by basically taking the field and writing the constant 1 times t and differentiating with respect to t. So you want to make sure that the derivatives at the at phi equals 0 in the constant field and in the linear field directions are
Vanish.
0.
At the origin. Okay, so these are my normalization conditions. Now, as an example, I said there was a remainder. And so the remainder, I've set up a notation because it's very heavy to write gamma, L, zeta, all that. So I'm writing that as R. Okay, because I've written Lx because SL, the scaling transformation, is such that the result will be, if that was an X, this would be an X. Okay? So J, I choose as my, the object I'm going to normalize is J, which is this R sharp minus this, where minus a relevant part to be fixed, so that, and the relevant part is chosen to be this, what I defined earlier, okay? And we fix the coefficient alpha p by imposing that J is normalized. Now, I didn't get a chance to write something more. That if you go through this procedure, maybe I'll put it in the slides. There's an explicit formula for these alpha p's in terms of these R sharps, what they should be evaluated, suitable derivatives evaluated in the origin. And these, it turns out that one has estimates for those things, Therefore, we have estimates for these coefficients. And this will control, these coefficients will control the remainder parts of the flow in the local potential. I do not have time to write this down, but so what is Q? So Q is a second, we call it the second order activity. So it is automatically generated in second order perturbation theory. And you can write, forget all of this, as the sum of three contributions. The W is the non-local total I mentioned, W1, W2, W3. And X is small sets, right? X is either a second order, that's all you can get. If it's a cube, then X tilde I define to be the cube times the cube. And if X is already a cube times the cube, X tilde I define. These are the integration regions for the two variables of the integral kernel. I mean, there's an integral kernel. Where is it? Now, so in this one, m is equal to 1, 2, that is delta, the cube, or cube times cube. And cube 3, 3 is the one which I've completely recorded. It's the 5/6 term, which you're asking about. Where is the 5/6 term? It's sitting right there. But it'll turn out to be an irrelevant 5/6 term, just by counting dimensions. Nevertheless, it will contribute. In the second order contribution, it will contribute to the flow. Okay? So I mentioned that the kernels W, I didn't write down the recursion relation. It's rather simple to write down. And it converges in some Banach space norm. It converges, it's an autonomous evolution. It converges to a fixed point, which is nice, and that's the fixed point function. I'll choose not to make the notation too cumbersome. So it speeds up the flow, that's all. So the renormalization group map is producing a discrete flow, where UN is a triple. I'm writing UN to be this triple, GN, MUN, and RN. Also, I could put in WN, but since it's fixed to be W star, I don't think about it anymore. It represents a point of the RG trajectory. And the renormalization group map produces a discrete flow, UN, F, UN, and its components of the flow are this. Gn plus 1 is the G component of the flow. And this reads, I'm working on L to the epsilon. Epsilon is positive. Epsilon, if you remember, is equal to, let's see, yeah. Epsilon is equal to the critical dimension, dimension minus, the D is 3 minus alpha, okay? Minus 2 alpha. So that gives epsilon. Okay. That's 4. So mu n plus 1 just works out, whereas for the standard case is L squared, now it's L to the alpha. Alpha is strictly between 0 and 2, and there's a G squared contribution, and there's a remainder, Cauchy bonds. And finally, there'll be an Rn plus 1, which is the nth direction, which is the art direction of F, the art component of F, which is UN. Okay. Now, over here, the coefficient A is positive, and B is also, I believe, positive. I'm not sure. Go to that. Yes, B. Not very important. So there is a fixed point. If you see approximate fixed point. If you forget these terms, these two terms, this term will have this term, sorry, okay, this, hold on. Okay, so if you forget the remainders in over there, then you can easily solve this for a fixed point, okay? So the fixed point will be equal to something L to the power of epsilon minus 1 divided by A. And that's of order epsilon.
Pronob, if you like, I can point at it.
No,
while you
I'm going to do it. I'm going to master this, actually. Don't worry. So, you mean you read my amanuensis? Or the laser pointer bearer? Okay. Okay, so get rid of this. So this is G bar order of epsilon, okay? So I'll be perturbing the flow around G bar. So if I define G tilde n as Gn minus G tilde, and Vn is equal to this triple, previously Un has been replaced by Vn, then the new relations are, this is a contracting factor actually, and plus In, this is still growing, and this is as before. Now gamma of epsilon is 2 minus L to the power is 1 minus order of log L epsilon is less than 1 for sufficiently small L with L fixed. So gamma of epsilon is what?
Epsilon, right?
Sorry?
Sufficiently small epsilon. You said
Where?
sufficiently small epsilon.
Yeah, sufficiently small epsilon.
Yeah, you said L.
Oh, with L fixed.
Yes, with L fixed, right.
Okay. Sufficiently small
So
epsilon.
it's a condition on alpha.
Yes, yes. Sufficiently, from the point of alpha, yes. Epsilon, I always forget this, will be equal to 3 minus 2 alpha, okay? So already there is a contraction factor over here, but there is, this stuff is there to mess it around a little bit. Now R also has a contraction factor which I write down. But the mu evolution is dangerous because it's growing.
Because?
Because it's growing. L to the alpha is growing. Exactly as I did for the approximate flow. It was right. It was, and when you differentiate it instead of 2, I put 2 alpha. Now, okay, so now I'll come to some norms before I go further to now analyze this. There was a mistake in our paper with David, a conceptual mistake. In fact, it was in some earlier papers also with David, with Demarcus, which thankfully Malik noticed actually. And I'll give you a repair job over here. It's a conceptual mistake. And Malik verified all our estimates were correct. At least one person has verified that all our estimates are correct. because he went on to do other things with them afterwards. So we know that the cutoff covariance we see is supported on the subspace of smooth functions. In fact, it's almost surely smooth, and we can construct the subspace by the usual version, by the usual procedure of taking the intersection of smooth function with the sigma algebra and S prime, and then restricting the exterior measure to that and showing that it's going to be additive. It's a standard procedure of constructing versions. This is in Helmholtz. Okay. But on this subspace, we can give various norms, subvolume norms, CK norms, etc. And thus producing uncompleted, we never complete, norms with the various norms. It doesn't mean that everything will be lost if I complete it, okay? They're not completed. So suppose you have a linear functional, which is, it could have been any closed field, but C, valued bounded linear functional continuously on CK, for example, CK of x. By CK of x, I always mean CK of the smooth functions restricted to x. Okay? That's what I mean. Considered as a norm space. Then its dual, topological dual, which is the norm of this, such that in this, such that U is less, CK is less than or equal to 1, is in fact defined in this norm, is a complete. The space of linear function, bounded linear functionals on a norm space is complete. It doesn't have to be a Banach space, but the space of linear functionals will be a Banach space. It's a complete norm space. It's a Banach space. Now that's proved. Maybe in the first few pages of Dieudonné or somewhere. Okay, it's a standard result in functional analysis. Yeah, that'll be important for what I do. So this corrects. In the paper that we've written down, they're not considered as multilinear functional, the linear functional on CK in the traditional sense, right? But CK of the smooth, norm space CK of smooth functions, okay? So that seems to be simplest way to do it.
So what? I don't understand. Originally, it was you.
Original papers with David with Bridges,
Yes.
Bridges with Dimmock and Hurd and
Yes.
so on, and there was an error, which was to consider the multilinear functionals
Yes.
as defined on the Banach space C2, for example.
Instead of the space of smooth functions with the wrong.
Yes.
Yeah,
Yes.
right.
This is the only change to do.
Okay.
Nothing else. Because what you're really interested in is the multilinear functional, bounded multilinear functionals in some sense, and it should be complete because we're going to apply a Banach fixed point theorem.
So this is just a larger space now. in some way.
Sorry?
It's a larger space than the dual.
Yeah,
Than the
topological
dual
dual
of C.
is always of a norm space. Topological dual is the bounded linear functionals on a norm space, right? And that's complete. Provided the completeness proof is completely provided the field which you're using is, they're valued in something, okay? In this case, they're valued in C, for example, the complex number. That's complete field, and that's all you need to use to prove Cauchy.
Yeah, but the activities you constructed, they didn't actually converge in the space
Yes.
that you used.
Yes,
They only converge in the larger space that Malik defined. So.
sorry. It's a complete space. I mean, I can prove that the bounded linear functionals valued in a field which is complete, right? On a norm space, I can send you the proof.
Yeah, okay.
It is complete. Okay, I sent Malik the proof. It's a trivial proof. Actually, Dieudonné in the first volume
Yeah,
of
that's
the,
not what I'm worried.
Maybe the question is what goes wrong if you use the actual CK spaces.
Oh, what,
rather than the
because I'll be
decimal
using
spaces.
Sauvignon spaces and so on. The CK spaces are only 3 times differentiable. Whereas maybe I need I need something much more to give Sauvignon embedding. I may need Sauvignon spaces of functions and derivatives, where how many derivatives will be dependent on this dimension D, right? D by 2 plus something that can be large.
I'm actually confused by this too, because I thought we wanted to work with the space of functions not necessarily linear on fields. I mean, for instance, the R that you're using here, the R is just a function on the space of fields.
Yes.
It's not necessarily linear. Or
I'm not
anything
saying
like
it's
that.
linear.
So don't we want to know that that norm is complete in order
No.
to do our fixed
No.
point theorem?
No,
No?
I want to create a norm on R. To create the norm on R, I'll have to take derivatives and so on and so forth, right?
Yeah, but doesn't that have to be a complete norm?
That is a complete norm.
All right, then we're happy if you're.
That
if
is
you're
a
producing
complete, because it's, you'll come to this in a second. That is a complete norm. Because it's from linear and multilinear functionals you'll be creating.
Well, okay, this makes my head spin. Let's just go on
Yeah.
before we get sidetracked, otherwise we'll never finish.
Okay.
There might or might not be a problem here, and I'll be happy to talk to anybody.
Well,
about
if it's a
afterwards.
problem, you must correct it. Okay, this is my solution. G, I'll come to, so G is so-called, in the old days, we are not using L infinite weighted, L infinite norms, but light field regulator is this. This actually measures how fast the fields, the polymer activities can grow. And we'll take the number sigma to be d by 2 plus 2. So already you see we need more than 2 derivatives.
Yeah, so, sorry, if maybe I can rephrase the problem, if I understood the solution. So the point is that there are really two spaces, no? There is the completion of smooth function with respect to the C2 norm, or C2 functions.
Yeah.
No. The,
And they are different, no? It's like L infinity and completion of C infinity function
yes,
with L infinity.
yes,
They are not the same space.
they are different spaces.
And in one you can approximate, in the other you cannot
Yeah,
approximate.
right.
So
That's it. That's all I'm
what
saying.
you want to do. So you need the smaller spaces because you need separability to
For
approximate.
example, you see it straight away here. I said that I
And
want
in L
to,
infinity is at infinity, sorry.
Yeah.
It's like C infinity with compact support. And you can complete in L infinity norm. Or you do L infinity function, but you can never approximate one with compact supported function in L infinity norm.
Right.
Okay,
I
so.
don't think that's the issue, but.
Yeah, but of course it's not at infinity, it's in the small scales, but it's the same issue. It's like you have the same issue with older space, like order 1/2 function or completion of smooth function in order 1/2 norm is not the same. One is you can approximate, the other you cannot approximate. For the same problem, but in the small scale instead of the infinity. In the sense that they can oscillate. So, for example, if you complete with order 1/2 norm, the smooth functions, the modulus of continuity is going to 0 anyway when it's smaller than square root, okay, when you go to 0.
must be, we'll
Okay.
we'll come to this. Okay? So there's a stability of this large field regulator. It says that this has not changed at all.
Sorry, Pronob, just
Yeah.
before we put this thing out of discussion, so that you can go on. My understanding, and I think it's certainly right, is that our mistake was that we used a norm on the space of, there's this thing called R, which is a function on fields. It's the remainder. You do your second order perturbation theory, which is, and write exponential of a polynomial, and then you put the rest as into these polymers. And so on these polymers you have functions of fields in the polymers. So we had a space of functions of fields which wasn't, and a norm on it, and the norm was not complete. So we couldn't really use a fixed point theorem for this space of functions on fields, even though we did. That was our mistake.
But the
Now
norm
Malik
is-
fixed it. Pronob is outlining another one, another fix, which I at the moment am confused by, because it's not just linear functions, it's all possible
All
functions.
possible, multilinear functions.
Well, just all functions, right? So anyway, you're going to tell us now what the norm is on this
Yes, you
space,
see that.
and we can then just
Yes.
see whether it's complete or not.
Yes. So we take a finite number of derivatives, and this is possible because of the finite range. What that end note is, we'll see. And then we can, this, if this is the case, then that we have proved is less than gkx5, that's the maximum work. The smallest c defines the norm, okay? Which is h followed by g. I think this was the difference between what we were doing earlier, that we first now take the h norm, and then we take the g norm. So there are also, I would like to measure the flow coefficients. The flow coefficients are numbers, okay? And they are measured by the so-called kernel norms, okay? Which is then evaluated at the origin. There's no question, since it's evaluated at the origin and the field is zero, you don't need a large field regulator at all. So in our problem we choose, basically we choose h as g bar to the minus quarter, g bar is the approximate fixed point of order epsilon, and h star here, L to the alpha by 2. But the definitions are quite independent of that. And our final norm is we measure the growth in sets. And basically the statement that large sets will contribute little. And I know there's something happened in my typing. This thing is floating around everywhere. Something, I haven't been able to get rid of it. I stared and stared and stared and stared. I can't get rid of it. Normally tech will tell me that there's something funny going on, Okay, so for the moment I decided not to worry, okay? So putting it all together, this has a G in it, okay? And the H. So this gives us a Banach space of polymer activities. Okay, this is a very nice property of this electrical exercise to prove that this weighting function that I chose, this A of X, right, over here, right, has the following property. That for all connected one polymers, that is polymers are based on unit blocks, I don't know, this is very, very strange, actually. This is very strange.
Maybe I could just see if I can do the pointing and.
No, I'll do the pointing.
Okay.
You sit down, David. Okay? This is CP8 L of X. This X bar of L is the L closure of X. It's the smallest L polymer connected which contains X, okay? But if X is large, okay, so if X is more, if it's a connected polymer, one polymer which is bigger than 2 to the D in size, then we have L to the, it should be 2 to the capital D probably, minus D minus 1, okay? This is a contraction factor there. And in estimates, this is because I'll be doing reblocking, and this would turn up. So it has the important property, large sets contribute contracting contributions to the fluctuation map. So all the subtractions that we're going to do are going to be on small sets.
So the thing is, a set with a lot of blocks tends to have fewer blocks after you close it.
Yes,
Look at the smallest set.
because
Big
L
blocks
closure
contains
is
it.
made out of L blocks, okay? L polymers, L closure that are very late. See, when I say L closure, the smallest connected union of L blocks containing X.
That will have smaller, so that when you take actually we should just draw a picture. Can I draw one?
Yes, of course.
Yeah. So, where's a piece of chalk? That's what we need here.
Everywhere.
On
the
the
blackboard. On the bottom
underneath.
of the blackboard.
Oh, right here. Right, okay. So, if you're in 2 dimensions, just because it's easier to draw a picture, when you take the closure of a set like this, which has 2 blocks, 2 small blocks
If
in it,
you in one block, you put it in.
or even one, right?
Yeah.
What can happen, I mean, if with this thing here is, when you pass the larger blocks have these division lines that, because it's like dyadic, for example, which might occur here. And in that case, the smallest large polymer that contains those 2 blocks would look like this big one and this big
But
one
you
here,
could,
which
you
is
could
2
have more blocks in here.
You could, right, but the
Yes.
point I'm making now is that this particular polymer did not get smaller when you reblocked it. But if, for example, you had once you have more than 2 to the D blocks, so in 2 dimensions, once you have more than 4 blocks, then no matter how the big blocks come in, you will have fewer blocks after you reblock it. And because of that one factor in that weighting in the capital A, you'll gain a small factor. So it's just automatically contracted if you choose that norm, the polymers that live on large sets.
So the D plus 1 is not important. Is important?
The D plus 1, is
It
it
is
2 to
important.
the D or 2 to the D plus 1? It's
See,
2.
this is 2 to the capital D.
Yes,
Or
so-
2 to the small d, I don't care.
So if you have more than 2 to the little d blocks, then then the polymer will look smaller and you will.
Yeah. No, but I mean the power D plus 1.
You
It's
have to
important
beat
or
the
not?
volume.
Or the power of L.
Oh, the power of L.
Or you just
Well,
you
it
need
will be. I will
like-
need some amount of this, in this estimates when I reblock.
Yes, because you want, when he normalizes, when you
Yeah, yeah.
define those normalization conditions, you gain a certain number of powers of L for rescaling reasons on the field. But if you choose this power like that, you can make sure you gain at least that much just from this effect of the larger polymers looking smaller after reblocking. So you make those irrelevant just by that choice of L. Yes.
No, not the choice of L. The fact
By
that there
the
is
choice
D
of
plus
D.
1.
Yeah, by the choice of D plus 1.
Okay. It's a choice.
It's
You
a choice you can make. You see,
It's enough.
there are, for instance, in one large block, there are L to the D small blocks. And so the entropy is L to the D. So if you get L to the D plus 1 into the weight, you beat that entropy.
Okay.
Whoops, we lost it.
we screwed up with the black.
The computer still have battery? Maybe the bright is out? 'Cause it's not saying no source.
It flashed off for a
Yeah,
moment.
it's coming.
No signal.
Ah,
No, never go. Sorry.
Mostly to the one.
So now I'm going to write down some estimates. I'm not going to prove them at the moment. So we introduced this norm, kernel norm, which is the one which measures everything at zero field, and there is Rn norm, okay, which I'm going to multiply by epsilon squared, g bar squared, if you wish. Okay. And we define a Banach space consisting of elements B. This is the deviation from the approximate fixed point, mu and R, with the norm epsilon minus 3/2 g tilde mu and R. Okay. Now this, if this is bounded, this will automatically give me a restriction, say by R or something. They'll just say that g tilde is less than 3/2. G tilde is a deviation, right? And mu is less than 2 minus delta that object, and R is that. The reason I put in the epsilon squared to measure everything the same way, because Rn, the bound, you lose a lot of epsilon in the bound, okay? So it's something like epsilon to the power of 3/4, again. 3/4 plus 1 plus 2, right, is 11/4. So I take an open ball inside the Banach space. So our next theorem says, and let the ball be of radius 1, which essentially means that each of the elements over here, components, is less than 1. Okay? The next theorem says, first theorem says, is stability. If Vn is E1, the ball of radius 1, then the flow correction to the flow the G flow, which is I tilde, which depends on all three objects, is epsilon to the 11/4 minus eta, and rho tilde, which is a correction to the mu flow, is that. Now Rn plus 1 has a contraction factor in this term, okay, which is L to the minus 1/4.
That came about from the normalization.
That came from the normalization, I guess.
As
Fixed
well,
phenomenon.
as well as the large set phenomenon.
Furthermore, we have okay. So all the operations we perform in this thing are analytic operations. The extraction, this, that, everything converges in series. And therefore we have, we can use Lipschitz continuity. And the Lipschitz, I'm writing on the proof. The Lipschitz condition is just, if you vary within the ball, B and B prime, then you have these things, these estimates. B minus B prime is the norm of B, and the norm of B minus, on the right hand side, is calculated the box norm that I gave earlier. Okay. So we have that. So now the idea is we write the flow equations as integral equations. If you write it as an integral equation, then G tilde of K has gamma epsilon to the power of K after K iterations, and 0 to K minus 1.
They're actually discrete interval.
discrete intervals, sums.
The sums instead of
Sums.
intervals.
So it's just okay. But for the mu, I'll do exactly what I did in the approximate calculation. I take the reverse flow. The reverse flow says that I've given all this up to n, and what is mu k? The reverse flow is that, okay? But then I make the same assumption as I made last time, which is, let us assume that mu n is uniformly bounded. And let's try to solve the equation. Okay? And if you do that, and let n tend to infinity over here, you'll get, this term will disappear. This term will disappear, okay? And you'll get this equation. You have to show, I have to now show that this equation has a solution and possibly a unique solution.
Sorry, I forgot what was VJ.
Sorry?
VJ is the full
VJ.
data.
Ah, the
The
full
G, the
data.
mu, and the R.
VJ.
Oh, Vj is the triple.
GU.
There's a deviation from the approximate G flow, G tilde, right? And then mu and R. I've gotten rid of the W as W star, so I'm not thinking of it anymore. That's what it is. Okay, so with that assumption that the mu is uniformly bounded, I got this. And this is a trick due to Irwin.
Irwin. It's a
Still very full theorem advanced.
standard dynamical systems
Yes.
trick, which is absolutely marvelous. It deals with an expanding direction by putting a boundary condition at the end of the trajectory instead of the beginning.
But this is what I haven't discussed is, you do for unstable fixed points. Wilson discussed unstable fixed points. Yang-Mills unstable fixed point, in Wilson's sense. There is it under iterations. Non-linear sigma model in 2 dimensions, unstable fixed point. And Wilson said it's only in that case that you need a renormalization. The renormalization should be is proportional to the number of unstable directions of the flow. The number of renormalization. And that is to stabilize the flow. And in fact, if you do the calculation for which I've done for non-linear sigma model in 2 dimensions of the angle, it's up to 2 loops, and that's a universal part. That's enough to stabilize the whole flow. So we have to solve this. So how will we solve this? Well, fixed point, you see. We consider Banach space V with Pn and E supplied with a norm. Okay? And E of R is an open ball of radius R in this Banach space. And we let the initial V0 to be G tilde 0, mu 0, okay? R has not yet appeared. Now theorem 3 says that existence of a global boundary, if you choose V0 to be a radius model of 32, okay, ball, then Vk, this iteration Vk that is in a ball of 1/4 for all k greater than or equal to 1. That's the theorem. Now, prove it. You write the renormalization will flow in integral form, as I said. Vk is Fk. F has components. G component, mu component, R component. Where the right-hand side is defined by the flow integral equations, okay? These things over here. So if we define the sequence, f of b is f0, b, f1, b, and so on, then the integral flow equation can be written as a fixed point equation. Capital V is equal to f of b.
So it's a fixed point equation for the whole trajectory,
So the whole trajectory.
not just,
This fixed point equation, B to capital F V, has a unique bounded solution under the conditions of theorem 3 by virtue of Lipschitz continuity. Now, I can give the proof, but I can put all those things in, okay? So what's a stable manifold? So if you have the map F, the renormalization map, the K-fold thing, the stable critical manifold is defined by it's the original V in the small ball such that Fk of V is in the ball 1/4. Okay? Okay. Now write V as V1, V2, where V1 is G to the R0 and V2 is mu, the expanding variable. Initially, V1, 0 is G tilde 0 and V2 of 0 is mu 0. Now theorem 3 says that for V in the ball 132, there is this for V, there is a V2 such that Fk of V is in ball 1/4. Okay, for all K. Now there's this consideration of Schub, I'm not going to go into it, that Ws of F is a graph of a function. V2 is h of V1 with h Lipschitz. Moreover, iterations of F restricted to this Ws of F contracts distances and therefore has a unique fixed point. Okay. This means also that we have the mu star, okay, is not 0, and the critical manifold in this case is a curve has been fixed. Okay, this B2 is HB1. B2 was mu, and B1 was G and R.
Sorry, can you go back one slide?
Yes.
I just wanted to. So it's clear that theorem 3 says that, or maybe I missed it.
Yes.
Yes?
Because if I go back,
Because you pick the initial data for the G and the R,
yes,
and then you can find the sequence
Yeah,
that starts from the G and R.
Where it's written.
theorem 2,
You go to the map on
There it is.
sequences.
where is theorem 3?
Yeah.
This is theorem 3, which is every time. Okay. So somewhere mu star is lurking around in this, okay? The fixed point. So the corollary of this is that this fixed point is non-trivial. Because if Vn tends to G tilde star is G star minus G bar is one of the coordinates of V star, then G star is not equal to 0, since, let's see where it is. V star is in this, and therefore G star minus G tilde is 1/4 of epsilon 3r, to the power of 3r. And we know that G bar is order epsilon, so G star cannot be 0. Okay?
G bar, it's the one you use.
G bar is approximately perturbing around,
That was the
G-bar.
approximate one, explicitly known.
the approximate fixed point, which we know.
Just by omitting all the remainders.
Okay? So that's a basic theorem. So in order to prove this, I needed a certain number of things. After all, I needed the basic Lipschitz continuity, and basically, and even previous to that, forget this, and this. These are just bounds for U, rho tilde, and xi tilde. Okay? Now, these were previous estimates, which I have given. And this is the correct thing to take up. One of the correct things to take up is based on earlier estimates. Okay. Which I can add what those are, those estimates are. And, I mean, I'm not going to prove all the limits because there's I've counted 17 of them. It's very discouraging.
Can I ask another general question?
Yes, yes,
So
yes.
at some point you do a second order computation.
Yes.
no? Why it works?
Second order.
Yeah, why
Because-
one never have to
Well, we have to start somewhere.
before.
We have to start
So are
somewhere.
you asking why it doesn't have to be third order?
Yeah.
You're good.
No, but why? Yeah, but
But why
even
is
in
second
Kupiainen
order?
paper is always second order.
Yeah.
It's never third order.
That's because once you've gone to second order, the flow equation for the coupling constant G has the form G is equal to, the new G is equal to the given G plus an order G squared correction. And anything that comes after that of order G cubed or
G
more
cubed is in the
does
remainder.
it can slightly perturb the trajectory, but G cubed is not strong enough to change the qualitative behavior.
And that's sitting in this thing that I called xi.
But here it's important that you extract from the R, right?
Absolutely,
Yeah.
yes.
Yes.
So, well, that's in a way of saying the same thing. So if you just look at second order perturbation theory, and then after that, and you solve that exactly for the trajectory and everything else, which you can if you want. If after that you add on these third order remainders
Yes.
coming from the R, the capital R, they, the theorem is that it's structurally stable under these third order remainders. So the trajectory will move a little bit, but it will there'll still be a fixed point, a non-trivial fixed point which
Non-trivial
it
fixed
goes
point.
to. So you cannot make the non-trivial fixed point go away with third order remainders.
Any more questions? Because I can put down more things, which I have not, right? And time, it's quite discouraging actually to sift through and what is essential,
Is there a transformation which implements this?
You mean really makes the remainder go away?
No, that it is like in Kam theorem, no? That you can perturb the tori, but there would be a map which maps.
So I don't know enough dynamical systems about that. I don't know whether Pronob does either.
No, but okay, you have some situation, no?
Yeah.
And then you perturb it.
Right,
And then you have a new situation, you say it's structurally stable.
yes.
So what I'm asking is they are made from coupling constant to coupling constants and polymer to polymer such that bring back the situation to the unperturbed one.
Yeah, I
see?
don't
I don't
know
know
that, I mean, that was a big issue for Smale, he discussed it a lot. I just don't know the answer to that. I mean, it's interesting, for sure, whether we could construct such a map.
You see, what Can did, if you go back, well, I got it, you're sitting on these normal, what do you call it? Action angular variables, okay? And you want to make these transformations. You did it in form of series, one very first. You put it in normal form, okay? In terms of phase and phase, okay? Normal form, p squared, q squared. So those series diverge, actually. Okay?
Yeah.
What you wrote down, and then Pronob came along. Okay. But there's a beautiful proof of Can, at least in the analytic case, in which you have a torus, I mean something in a torus which can be solved, right? Plus the perturbation, and the perturbation is analytic in some parameter. You see, Moser, upon Moser solved it also for C infinite condition, or C2 condition, C3 condition, but the analytic case. Now, for this analytic, I mean, one of the reasons that the series diverge is the so-called small denominators problem, okay? And Galavati showed that for the analytic case, that the resonances cancel out in some sense. But Gavensky and Kupianin have a beautiful proof of this by iteration, right? Some kind of renormalization loop iteration. Because there is no resonance, right? If the frequencies satisfy something called the Dipole-Time condition, and then the whole question is, well, put a cutoff there, and slowly lift the cutoff away. And there's a very beautiful paper, 20 pages or something, 30 pages at most, where they prove this Can theorem for without going through a big series. Lindstedt series,
Yeah, actually, it's the
Yes.
renormalization group.
You must have done the Lindstedt series. Did you do this long series with Galavati?
I've read both the paper of Galavati and that one of Gavensky.
Yeah, which one's shorter, tell me.
Yeah, I mean, it's short. It's using really renormalization.
Furnish reminded me that Galavati thing is based on Eliasson.
Yeah,
Eliasson,
yeah, that I didn't read.
yes.
But I think Galavati paper is clear enough, but okay.
Is what?
It's clear, but okay, there is the part where you see that there is no conceal, there is also the initial part, it's analysis, but then you have to show that something does not happen. I don't remember anymore what was. That this small denominator does not
Yes.
cause a problem. And that was true.
What's happening here?
I think we are too slow for the computer. No, I think it's the computer.
Is it
Yeah, it's okay. It's coming back.
It's coming back. So,
So-
anybody else have any questions while we're having this discussion, an abstruse discussion of dynamical systems?
Well, I rather like it, actually.
Well, I do too, but there may be other people who are confused about other things.
No, but I think you can get a better picture if I actually use the Lipschitz.
Let me ask another. So
Yes.
this technology, of course, works in dimension higher than 4 to prove triviality.
Yes,
It's easy, no?
it's easy.
Well, actually, I mean, so we did the proof in 4, and we promised that we would be soon writing the proof in higher than 4, and we've never written it because it turns out to be annoying. So I don't know at this point whether one can
Exponential
really
convergence.
say it's
The-
easy.
Gaussian fixed
There's a
point.
strange problem, which is that so it is easy, for example, in 5, but if you go up to 20 dimensions,
Is it
there are a
discharged
very large
computer?
number of,
Sorry?
if you go up to a very higher dimensions, there are irrelevant terms like, well, there are gradient terms which are like things with 3 or 4 gradients in them, and things like that, that seem to require some special treatment. So I'm not so sure that we were wise to promise that we would be rapidly writing the higher
But you
dimensional
should be able
version.
to do it, because also the dimension, let's say dimension 5. Okay?
Yeah.
Now dimension d minus 2 by 2, right? That's equal to 5 minus 2 is 3 halves, okay? The field is 3 halves, and 5/4 in that case has dimension 3 halves times 4, that's 6. It's irrelevant, okay? 5/4 is relevant. You can start putting in some gradients also, I think. How about grad phi squared, phi squared? Do I have the leeway? I'm not clear. It's not clear. Because 5/4 already had, we said it was 3 half times 4, that's 6, right? And then if you put in 2 gradients here, you make it even more irrelevant. That's clear.
Yes, but anyway, the actual procedure, the way we wrote our papers, might have been stupid for doing higher
You
dimensions.
kind of have to keep all terms that are at most as irrelevant as the phi fourth
Fourth,
term,
that's
and
the
since
problem,
it's extremely
right.
irrelevant, there will be a lot of gradient terms and the phi square terms that are
So,
not any more relevant than
so we probably didn't do it in a good way for doing higher dimensions easily, even though it actually is conceptually easier.
Oh, yeah, must be on. Maybe we should put up the light.
No, it does not work anymore.
Why?
I think it's too late. He decided not to work. Yes. I think you moved the blackboard. That's also.
Yeah. Okay.
Some-
Ephemeral.
Okay.
It seems to be back.
The full screen is.
So the next thing I want to discuss, well, I can put in some more details in this, okay? He's doing something, okay? I can, and I discuss the correlation function also. I can discuss what happens. That is in the continuum limit, why? You know, there's a scale dimension that is being put in. The scale dimension is dictated by the Gaussian for this alpha case. Okay. If you control the renormalisation group trajectory,
Before we get to the correlation functions, so this non-trivial fixed point that you've constructed here,
that you also
Yeah,
contributed to.
maybe not everybody understands what the significance is. So, Pronob gave an argument that the coupling constant could not, in front of the 5/4 term, cannot be 0. And that's true, so it's not trivial, that's good. But it's actually very non-trivial because it has all of these corrections that come from the R as well.
Yes.
If you looked at it, at the effective action for this theory, it would be a very complicated function of all of the fields. Non-trivial means not Gaussian, and it's really not Gaussian in this sense, that it has all of these corrections. And so now, with the correlation functions he's about to do, you can talk about linearization around this non-trivial fixed point and compute lots and lots of critical exponents. And actually, Ajay, you
Phi squared. We should do a talk on phi squared, actually.
things like that, yeah.
That had never been done before. Ajay, in his thesis, constructed in the hierarchy, for simplicity, let's speak, the hierarchical recursion, which is a finite dimensional recursion, the field phi squared at a point. The scaling field is not the field that you put in. For instance, from the point of statistical mechanics, over here, the scaling field would be something like L to the n phi is not yet the scaling field. L to the n x. And you have to find out what phi is, that this thing has a limit in the sense of insertion in correlation function, for instance, weak limit. That would define the limit of this in weakly would define phi SC. Now, just as in this case, it's relatively trivial to construct this limit, at least in the continual limit that I was talking about. It is the same thing as dictated by the Gaussian. After all, the renormalization group trajectory I proved is a bounded trajectory. With this scaling, I had to scale it. This was scaling. But in general, it may not be the case. In other words, in general, phi may acquire okay, let me think of d minus 2 by 2. D minus 2 by 2 must be done in no about it, plus eta. And you must need eta at a fixed point. To get the limit exists. Similarly, if you can consider a composite field, now in this problem, this is d minus alpha by 2. And d minus alpha by 2 is dictated by the Gaussian. So you would expect that that is I'll show you, that in the correlation function, this is the dominant part that comes in, and then there's a contribution which goes down. Now, eta is 0 here. So one of the defects of this model, it doesn't produce eta. It produces other things. What sort of other things can it produce? And this is where we want to construct other scaling fields. Consider what could replace phi squared L to the n x L to the n some other object, and this would be twice d minus 2 plus gamma, not the gamma is a critical exponent, but I have to write something down, okay?
D minus alpha.
Alpha is already there. Okay. Oh, d minus alpha, you're right. D minus alpha plus something, okay? I don't know, what did you call it?
I mean, we call it like v sub phi squared or something.
V sub phi.
V sub phi squared.
Okay, anyway, whatever it is. So something. Okay, that's the name. Now, I had computed actually the fixed point in epsilon expansion around the fixed point, that it was something of the order of epsilon, right? But Adai and in a thesis, with work with Malek, and proved that there is, in fact, this exists, the hierarchical recursion is equal to something which is of the order of epsilon. I think you computed the coefficients and so on and so forth.
It's like
Right?
epsilon over 3 plus
Huh?
some higher.
1 over 3 or something, plus, okay? And that's rigorous. So that's the only computation that I know where, from a mathematical point of view, aside from solvable models, okay? Aside from what form of bootstrap or Slava, okay, and so on, that phi squared has been constructed. And that's very interesting. You should do a seminar on this, actually, in my opinion. Because not many people know it. You see, your result is buried in this vast paper. And I told Malek, Okay, that's all. But extract out just this part, the hierarchical discussion on this part, and publish it. Because nobody's done it before. Is it published, your paper?
He's
Is it
still,
still in the archives?
he's still in the archive.
Yeah, because you got pianic stuff and this and that, I mean, people get lost.
Yeah.
Whereas this, everybody would be interested, in the mathematical physics community.
The dynamical
But-
systems.
But Malik is quite an obstinate person, so.
Okay, we should,
Yeah.
let everybody who wants to leave have a
Okay.
chance to leave
Yeah.
here.
I'll do a short talk on Friday, okay? And clear up the things which have not been cleared.
We can ask a lot of questions
And-
anyway.
Is the video off?
Not yet.
And ask more questions, and